So you show up to a really big party. What's the first thing that you do? Well, if you're anything like me, you're going to enter the party and scan the crowd. You're going to look around to see who's there because you want to interact with the best person that's there, right? Well, atoms and molecules, well, they're like people too. And when they show up to a reaction or a party, they look around the beaker to see what's there and they look for the best thing that they can interact with. And that's true in most chemical reactions. It's also true in buffers. And today we need to talk about buffers. Hi, everyone, and welcome to this episode. Today we are talking about buffers. And if you're here watching this video, and I'm very glad you are, you're probably recently sitting in chemistry class learning about buffers and thinking, wow, there's a lot going on here. Or maybe you're brushing up for an exam, or if you're here for fun, that's extra nerdy too, so we love that. But we're going to talk about buffers a little bit. We're going to start by talking about what buffers are and how do they work, calculating the pH of a buffer, and calculating the pH change when acid or base is added to a buffer. So we're going to do some problem solving here, a couple of pause the video moments maybe, and we'll get into it. I have here a flask that has some pure distilled water in it, and I've got my pH meter in there, and it's registering nicely right under 7, around a pH of 7, which is what I would expect for some pure water. Now, what I would also like to do to it is I'm going to add some hydrochloric acid to it. This is a dilute hydrochloric acid with about 0.2 moles per liter. Get like 3 drops in there. And wow, already my pH is down below 5, below 4, below 3 even. That was 3 drops of hydrochloric acid around 0.2 moles per liter. So that is a big, big change in pH. Let's add a couple more drops just for fun. That's 3 more drops. Get it spinning around there. And now I'm down into the 2s. Wow. So now I have a solution that's pretty strongly acidic after only 5 or 6 drops of acid has been put into it. Okay, let's compare that to, give it a quick little rinse, to a buffer solution. And okay, right now we're back up to a pH of around 6.9, right under 7, which is good enough, I think, for what we need to see. Okay, let's take some hydrochloric acid and drop it in there. That's actually a whole big squirt. So a little bit more than 3 drops. All right, so I'm adding acid, and wow, my pH is barely changing at all. Let's add a whole squirt full, just for fun. All right, a whole squirt full of acid, and I'm only down to 6.74. It's a little bit of a change, but it's not very much of a change. So, what is a buffer? Let's just start with some general ideas about buffers. A buffer is a solution that resists a change in pH when acid or base is added to it. We saw me dumping some hydrochloric acid into a pH 7 buffer, and the pH didn't change much at all. It didn't stay perfectly the same, but it didn't change much. And that's one of the properties of buffers. A buffer in general needs to contain a weak acid and its conjugate base, both in fairly large amounts. Okay, and we're going to see why as we get going. Now, if you have not yet watched my videos about calculating the pH of weak acids or the pH of weak bases or the acid-base properties of salt solutions, you may want to go back and visit those videos first because this is where it all comes together and we have to think about weak acids and their salts at the same time, or weak bases and their salts at the same time. So quick little picture for fun to kind of get us back into thinking about them. This picture represents an aqueous solution of acetic acid, which is a weak acid, and it would have a pH somewhere down around 2 or 3, in this case 2.7. And the pH of sodium acetate, which is its salt, the acetate ion is the conjugate of a weak acid, so it's going to make the solution slightly basic, and we might have a pH of 9. Now, what would happen if you mixed those two solutions together and in roughly equal amounts? So you would get a mixture of the acetic acid, the weak acid, and its salt, and the pH here is registering somewhere in the middle, as we might expect, somewhere in the middle between 2 and 9. And so it comes out around 4.85. Fun fact, that 4.85 is very close to the pKa of the weak acid in question, which is the acetic acid, which has a pKa of 4.74. And that's one of the themes about buffers. If you have your components, your weak acid and its conjugate, in roughly equal amounts, your pH is actually going to be very close to the pKa of your weak acid component. So keep that in mind. as we go on through the rest of the video. So how does a buffer work? I have a couple of representations that hopefully will help to show how a buffer does both. It's able to absorb acid and base without a measurable change in pH. So here I have, pictured in the middle, a buffer. And it's got a weak acid, so far it's generic, HA, and it's anion, and they're in equal amounts, 4 of each in my drawing. And if you add hydrochloric acid or some other acid, let's get some protons in there. In fact, let's drop in a couple of protons, okay, that were not there before. What are those protons going to do? They're going to drop into the beaker and they're going to look around to react with the best base available in the solution because they're acids. And so what they'll do is they'll look over and they'll see these little anions floating around, and they're going to hook up with those anions, the conjugates, and they're going to make 2 more acids that weren't there before. Now, what we've effectively done is changed a strong acid, a proton, into a weak acid that's now part of the equilibrium, and we kind of got it to kind of neutralize some of its strength, and now we just have more of the weak acid that's part of the equilibrium. Okay? Contrast that to what happens when, let's say I put a bunch of OHs in there. Let's put 2 more OHs in there. Okay, we drop some OHs in there. They get into the party, they start looking around to see who's there, and what they find is they want to react with the strongest acid available, which is the acid part of the equilibrium. And so the OH is going to react with the acid to produce a water that wasn't there before. And the other OH is going to react to find another proton. Let's grab that one over there. And it's going to make a second water. And now you just have a couple of anions that weren't there before. So what we've done is taken a strong base and effectively converted it into the weak base that's part of the equilibrium. Here's another representation that I made because you're likely to see these molecular models, drawings of reactions and buffers in your chemistry travels. So it's the same kind of thing. We've got some weak acid, 4 of them, and 4 of the conjugate bases, the anions. And if I drop in a couple of protons, like these little guys, what they're going to do is look around for the best thing that they have to react with, the best base available. And so each one of these is actually going to grab onto one of the conjugate bases to produce 2 more of them that weren't there before. And so effectively taking the proton, which is a strong acid, and changing it into its weak acid. Okay? And if I do a similar thing with some base, drop in a couple of hydroxide ions, what they will do, just like anybody showing up at a party, they'll case the joint, they'll look around and see who's there. They want to react with the best acid available, and so they're going to see these weak acids and actually grab their protons to produce a couple more water molecules that weren't there before. So effectively taking the strong base and neutralizing it, it becomes water and a little bit more of the weak base anion. So in doing both of those things, reacting to whatever you put into it, if you put in acid, it'll react with the base. If you put in base, it'll react with the acid. And in so doing, it effectively limits the amount that the pH will actually change. So I put this in words on the next slide, so take a moment and check it out if you want. Note, it is assumed that the concentrations of the weak acid and its conjugate are pretty large compared to the acid or base that you add to it. No buffer is perfect. There's something called a buffer capacity, how much it can hold before it really kind of gets destroyed. We'll talk about that in a later video, but as long as there's plenty of these to go around, a little acid or base is not going to change the pH much. Added OH reacts with the HA to make more A-. Products are the water and the anion. Essentially, all the OH is converted into the anion. Added H plus reacts with A to make HA, the weak acid, since A- is a strong base. H plus does not accumulate, so the pH doesn't really change that much. Okay, so we need to get into some problem solving because you're going to probably have to solve problems based on the pH of buffers. And I want to start with this one. This one's already done for us because we've already done finding the pH of salt solutions. And this is kind of a repeat slide. If you have not seen that video on salt solutions and their pHs, you should go back and check that out first. So the pH of a 1 molar solution of HF, the weak acid, is 1.56. Okay, we've established that a while ago. what is the pH of a solution containing 1 molar NaF? And so we have a salt solution with its conjugate base, the F minus ion. So I set up the equilibrium. The F minus ion is going to go with water and reproduce some of the weak acid and some hydroxides. And we set up an ice table. And because this is acting like a base, I need the Kb value for the base. I know that the Ka value for HF is 7.2 times 10 to the minus fourth. So Kw over Ka gave me this Kb value. I set it equal to the equilibrium constant expression, solve for x. And if you need help on that, go back to the previous videos. And x is the OH, which is 3.73 times 10 to the minus sixth, POH of 5.43, and a pH of 8.57, which makes sense. It's above 7, and that's because we had the conjugate base there. All right, so now let's mix it up. So a buffer is a solution that has the weak acid and its conjugate in it in pretty large amounts. So let's calculate the pH of one of those. Related question, what's the pH of a solution now containing both the 1 molar weak acid and the 1 molar conjugate base? Okay, so here's what you're going to do. You're going to find the weak acid that's there, and I would set up the equilibrium that it would normally try to set up in water. And please note, I'm actually going to solve this problem a couple of different ways. So if you're looking for another way of doing this, hang on, just give me a couple minutes. So here we go. In our ice table, we're actually going to have 1.0 molar of that and 1.0 molar of that. So, sorry, that should be at H3O plus. And essentially 0 of this to beginning. But even though it's 1 times 10 to the minus 7th in a pure water solution. Now, I know it's going to go to the right because we need to make more of those to set up our equilibrium. So 1.0 minus x, 1.0 plus x, and x. Okay. So we're going to set the Ka value, which is 7.2 times 10 to the minus fourth, equal to the products over the reactants. And let's just go ahead and write the equilibrium constant expression, just so we're clear about that. Okay, so that's going to be equal to 1.0 plus x, x over 1.0 minus x, and that's equal to 7.2 times 10 to the minus fourth. Okay, so what I'm going to do is make an assumption that we've made before. There's 4 factors of 10 difference between the starting value here and the k value, so I'm just going to go ahead and erase or ignore these x values. So let's get rid of them, which simplifies things a lot, because now we have 7.2 times 10 to the minus fourth equals 1 times x over 1. That's easy math. That cancels also. So x is equal to the H3O plus concentration, which is equal to 7.2 times 10 to the minus fourth. And the negative log of that is the pH times 10 to the minus fourth. And that gives me a pH of 3.14. Nope, it's not actual pi, but it's kind of a nice coincidence that it comes out as 3.14. So that's great. So here's an important note about this. 3.14 is the pH, right? And we've learned about pKa, which is the negative log of the Ka value. And so the pKa is actually also 1/4, or 3.14. I'm sorry about that. And we get this situation that happens a lot in buffers where the pH of your buffer, because it has both, is actually equal to the pKa when both concentrations are equal. So if you have a buffer, any buffer, and you have the weak acid in there and it's the same concentration as its conjugate, or weak base and its conjugate, you'll get a pH that is equal to the pKa of your acid. And that's a nice way to sort of simplify things. And keep that in mind because we're going to see that a lot. Okay, so let's keep moving on. And just for fun, we're going to actually now calculate the pH change that happens when that buffer is messed with. So we're going to mess with the buffer, and in fact, we're going to calculate the change in pH when 0.01 moles of NaOH is added to 1 liter of pure water. Let's just do pure water first. Okay? And basically what that means is if I'm dropping 0.1 moles in 1 liter of pure water, and sodium hydroxide is one of our strong bases, that means I'm going to have 0.01 moles per liter of the OH concentration. Okay? And because that is 0.01 moles per liter, the pOH is just the negative log of that, which is equal to 2. And then the pH is going to be 14 minus that, or 12. Okay, so just think about a liter of pure water, you dump in 0.01 moles of NaOH, and the pH shoots up to 12. We've seen that the pH shoots up very rapidly when you have pure distilled water. All right, now let's take a moment and calculate the pH change when 0.01 moles of NaOH is added to the solution in example 2, which is our buffer solution that has hydrofluoric acid and sodium fluoride in it. Now, first of all, there's a bunch of steps you got to do for these, and one of the first things is to figure out what reaction is going to occur. So if I'm adding OH to my buffer solution, remember those OHs are going to drop in, they're going to case the joint, and they're going to look around and see who's there, and the best thing they have to react with is the acid. Okay, so we'll get those hooked up there. And they're going to react with the acid. Let's get the... So the HF is actually going to react with the OH, and we're going to give a single arrow here. It's basically a straight line shot. And what it's going to do is it's going to make some water and some more of the fluoride ion. Okay, let's do some stoichiometry. We'll actually do two ice tables here. So initial, we actually had 1.0 moles per liter of this and 1.0 moles per liter of that. Okay, and then what if I add 0.01 moles per liter of that? It's that many moles in 1 liter of the solution. This is actually going to go to completion. So this is going to go down by 0.01 because it's a 1-to-1 ratio, down by 0.01, and then up by 0.01. Okay? And I'm going to do an F here because it's not at equilibrium, but we're going to get our final concentrations here. This is going to drop to 0.99 moles per liter. This is going to go up to 1.01 moles per liter, and this is going to essentially be down to 0. It'll react completely. Okay, so these are our new concentrations of the two things. Okay? Then what I'm going to do is I'm actually going to go back to my equilibrium constant expression. The Ka, 7.2 times 10 to the minus fourth. It's now going to be equal to 1.01 times x and 0.99. And I got rid of the x's that those would change by. But now we have these two things, okay? So if I do the math again, I get the H plus concentration, and I get a pH of 3.15. Okay, I went ahead and solved for x, which was the H3O plus concentration, took the negative log of that. I get 3.15. That's not much. Whereas in pure water, my pH shot up by 5 pH values. This went up by 0.01. All right, so we're talking limiting the change in pH, and that's how they essentially do it. So if you think that all this is kind of complicated and there's a bunch of steps to it and it's a lot, well, you're right. But thankfully, a couple of scientists who have gone before us have kind of simplified things for us. And here we enter and meet the Henderson-Hasselbalch equation, sometimes called the Henderson-Hasselbalch equation. And it's a nice way to simplify buffer calculations, okay? And it's derived. You can look up the derivation on the internet. That's not that important. You'll usually be given this type of formula if you need it on a test or something. But what we figured out was that the pH of a buffer, pH of our buffer solution, and you can only use this for buffer solutions when you have significant quantities of both the acid and its conjugate base, okay? If one of these is essentially 0, you get really wacky numbers and it doesn't work. But if you have a buffer, think to yourself Henderson-Hasselbalch, because the pH of that buffer is going to be equal to the pKa plus a correction factor, which is the log of the conjugate base over the acid concentrations. Okay, you'll have this, remember it, write it down, and use it. If you ever see the word buffer, immediately start thinking about this because it saves you doing some bunch of ice tables sometimes. And so let's see how it works. We're going to go back to the same question as before. So we're going to get the same answer as before. So just bear with me. But I want you to show and see how it works. So if I think, oh, I've got a weak acid and I've got its conjugate. Okay, I'm thinking buffer, I'm thinking Henderson-Hasselbalch. pH equals the pKa plus the log of the base concentration over the acid concentration in your buffer. Okay? And so the pH of my buffer is going to be equal to the pKa, which is 3.14, plus the log of the fluoride ion concentration, which is 1.0, and the HF concentration, which is also 1.0. And so my pH, if you take the log of 1, you get 0, and so the pH equals 3.14, which is equal to the pKa. Okay? And you can use it also in our second example when we use this and we found out what happened when the some acid or base was added to this. All right, we added some, we got new concentrations. So the pH equals 3.14 plus the log of, if you were writing this down, you would have gotten 1.01 molar concentration of the fluoride ion and the 0.99 molar fluoride HF concentration after a little bit of OH was added. Okay, and if you get 3.14 plus the log of this value, which is 0.01, so you get 3.15. So you can use this. It's the easiest to use if these concentrations are the same, but if they're not the same, it's okay. Just plug them in, take the log of that ratio, and add it to your pKa value, and you have your pH. So it's a beautiful equation. It's wonderful. Like I said, you'll probably be given that equation on an exam. All right, let's look at another quick example, and then we'll have a pause the video moment. All right, let's say you're presented with this question just out of the blue. Calculate the pH of a solution that contains 0.75 molar lactic acid. I'm not even sure the formula of that right now, but Ka is given to me, great, and 0.25 molar sodium lactate. So I'm seeing the acid and its conjugate in here. So I'm thinking, I got both. I'm going to do Henderson-Hasselbalch. pH equals the pKa plus the log. It's always good to write down your equation you'll be using generically so that anybody reading your work can know that you know what you're doing. We're going to put the lactate on the top. I don't know, maybe you don't know the formula of that. I have an idea. It's got carbons and hydrogens and oxygens in it. But if I don't, I'll just abbreviate, and we'll put the H-lac on the bottom. What's most important is the ratio between them, not necessarily the chemical formula. All right, the pH is equal to the negative log of this value, 1.4 times 10 to the minus fourth, plus the log of the ratio of the two concentrations. So the lactate goes on the top, that's 0.25. The H lactic acid goes on the bottom, 0.75. And I'm going to get a value here of 3.85, which is the pKa of that, plus a negative 0.48. This is going to happen sometimes. You're going to get a negative when you take the log of that ratio. And my pH is 3.37. All right, and you should ask yourself, does this make sense? Okay, and if these two were originally the same, my pH would equal my pKa, which is 3.84. But if you notice, I have more acid than I have base, and so the pH is slightly less than the pKa, and that makes sense to me. So if the base were higher, then the pH would be slightly higher than the pKa, but in this case, it's 3.37. Okay, now pause the video moment for you to try. Calculate the pH of a solution that contains 0.25 molar hypochlorous acid, there's its Ka value, and 0.75 molar sodium hypochlorite. Take a moment, pause the video, see if you can solve this using the Henderson-Hasselbalch equation, and see you back here in a minute. All right, my solution looks like this. pH equals the pKa plus the log of 0.75 over 0.25. So this time we have more base than acid. The pKa of my HClO is 8.48. And I'm going to take the log of 3, which ends up being a positive value. So my pH ended up being 8.96, which makes sense to me because there's more base than acid in my buffer. Okay, we're going to end with a couple of solutions that are already worked out, okay? And because I just wanted to show you something else. There are actually two versions of the Henderson-Hasselbalch equation. You might be given one, you might be given both. But let's take a look. Calculate the pH of a solution that contains 0.25 molar ammonia. We've seen that before, and it has a Kb value of 1.8 times 10 to the minus fifth. And it's salt, ammonium chloride. So in this case, we actually have a weak base, and it's conjugate acid. So what changes? Well, not much changes. The formula of the actual Henderson-Hasselbalch equation stays about the same, but check how it's different. We're actually going to be finding the POH equals the pKb, because now we're acting like a base, plus the log of the acid over the base. The ratio has flipped because we're going in reverse direction with the base. Again, the derivations are online. Go check them out if you want, if you're extra nerdy. And the POH is going to be equal to the negative log of this value, 4.74, plus the log of the acid over the base. This is the acid because it's got the extra hydrogen, and this is the base down here at the bottom. I got a value when I did this of 4.94. Okay, and that's the pH. Okay, that's the POH, not the pH. So I have to subtract from 14 to get the pH, which is 9.06. Okay, and that's that. So I wanted to make you aware of this version of the Henderson-Hasselbalch equation. So check that out and write it down. And now let's calculate the pH after 0.05 moles of HCl is added to the 1 liter of the solution we just looked at with the ammonia and ammonium in it. Sorry about the scribbles. I had a little calculator misfire, but we corrected it. We're all fixed now. Just, try not to hate me too much. But the acid is going to go in, and it's going to look around the party, scope it out, and see who am I going to react with? Who's the best base available? And that's the NH3. So we're going to have a reaction of H plus NH3, making NH4 plus. 0.05 goes in and reacts to completion, bringing this down by 0.05 to 0.2. There's my calculator misfunction. And this goes up to 0.45. I plug them into Henderson-Hasselbalch with this version again, the POH version. The POH came out to be 5.09. The pH is now 8.91. It was 9.06 before I added the acid. It has now dropped to 8.91, which makes sense to me because I just added some acid. But that would be how you could use Henderson-Hasselbalch to simplify a little bit of your equations. Again, don't do as I do here. That was not my best work. But I'm hoping that you're seeing your way through some of these buffer calculations. You'll probably see a bunch of them. If you have any questions, you can send them to me in the comments or directly. In the meantime, happy buffering, happy problem solving, and have a great day.